So good morning, everyone. Thank you for this opportunity to be able to present in front of you today. I'm feeling a bit soft. Can everybody hear me clearly? All right. So my name is William. As you can see here, I'm part of the organization called Sangfor. I'm part of the product marketing and product management team. Today, I'm going to talk about how we actually use AI in our technology and what do we mean by, why are we talking about purpose-built AI? So let's just take a quick look at what we'll be talking about today. Why AI? Of course, that's one of the biggest trends that everybody's talking about, not just us in the cyberspace, but also in every single industry as well. We'll take a look at some basics. Now, I'm no expert in AI by no means. I'm just a messenger here today, but just to share with you some of the things that we've seen and that we've done in the field of AI and how we've actually applied it into our technology. We look at some of the purpose-built models and what are the use cases for it, and then finally some takeaways where I will share with you what's next for us in AI. So first of all, why artificial intelligence? Now, it's no secret anymore that cyber attacks are becoming more and more easy to perform, right? Whether it's a script kiddie or whether it's an experienced hacker, we are seeing a lot more cyber attacks happening, and a lot of it we are starting to see is actually very relevant to AI because attackers are also starting to use AI as part of their portfolio when it comes to attacking any of their victims, right? You can see here in the slide some of the more common use cases that attackers are using, leveraging AI to actually make their attacks more devastating, more costly. In fact, if you scan that QR code, it actually leads you to a very interesting article that was written by another company where they were actually able to circumvent some of the controls implemented on ChatGPT and finally make ChatGPT write them a polymorphic malware, right? So that's how dangerous it is right now. It is very easy for anybody to become an hacker because we're talking about things like ransomware as a service. We're talking about things about where you can actually go to the dark web, subscribe to any sort of ransomware, and then be able to use that to attack. But now, this ransomware as a service, similar to technology vendors like us, they also improve their technology. Why? By introducing things like AI, allowing them to be able to circumvent a lot of existing technology controls that you may be using today, right? Let's take Revil, for example. It is said that Revil's malware is able to detect whether the environment that it is installed in is running on Russian language or not to decide whether it needs to attack. So how do you decipher that? Again, some sort of AI model or AI capability that was built into it. So it is a very, very real situation right now. So for us to be able to effectively overcome these type of situations, one of the things that we need to understand is that when we see these type of attacks, very often there are patterns to it, very often there are trends to it. The problem is, a lot of times, relying on technology or the traditional technology alone, it will not be able to pick up all these trends. It will not be able to pick up all these behaviors. But it is something that us human we can do, leveraging our own human intelligence, our logic thinking. We are able to do this. Hence, the need for artificial intelligence, or what I like to call synthetic logic. Basically, mimicking our thought process using the available technology today to be able to pick up these trends, to be able to pick up these behaviors, and be able to effectively detect specific use cases. All right? So, before we go into what are the use cases, let me just do a quick touch base with regards to some of the technologies or some of the machine learning algorithms that we have implemented. So we talk about, first of all, okay, before I go any further, anybody doing study or is an expert on AI here right now? Raise of hands. You are? Please do not call me out. All right? So we first of all have unsupervised learning, which essentially is very useful when it comes to recognizing common behavior or common features. All right, so what it basically means is that we feed the algorithm a whole bunch of data and we let the algorithm pick up the commonalities among all the data that we have fed in, allowing us to be able to create classifications or groups. But the thing is, with unsupervised, it's not as effective because at the end of the day, the output of it, you still need someone to come and verify whether these are cyber attacks or not. Right? Good, you're nodding. Then we have supervised. So supervised overcomes the unsupervised in the sense that You feed it data. These are samples of malware, sample of APT, sample of ransomware. You give it labeled data for it to process, and then you feed it all your input. It will be able to correlate or cross-relate between your input and the data label that you have given it, giving the output that you require. The problem with supervised is that it is very resource intensive in the sense that us humans will have to play a very big role in terms of giving it the labeled data, right? So then we have finally the semi-supervised algorithm, which essentially means that I give the algorithm some labeled data while I ignore the rest. But when I feed in input into the algorithm, it will be able to use the labeled data to classify some of the input, but at the same time, doing what it does for unsupervised, be able to classify the rest as some other collection of inputs as well, and finally come up with a more valuable output, if that makes any sense at all. Right? So essentially, based on this set of algorithms, we have built a bit of use cases that we have purpose-built targeting specific behaviors or specific attack behaviors that we have seen throughout all our install base. Now, one of the things that I have to note here is that these are use cases that we have actually implemented onto our network detection and response platform. So we're looking at it from a network perspective primarily, all right? So today, we will talk about these 5 different detection mechanisms and some of the more common use cases that we can actually use these detection mechanisms against. So as you can see here, we have things like DGA, domain detection. Anybody heard of DGA before? Domain generation algorithm. It is something that malware uses. We'll talk about it a bit later. We've got encrypted communication modeling. We've got encrypted brute force detection. Malware and ransomware protection, that's probably the most interesting use case that everybody's interested in because everybody knows malware, everybody knows ransomware, everybody's afraid of ransomware right now. And then finally, we talk about UEBA, which is probably one of the most common use cases of AI that has been around for quite some time, all right? So let's go straight into it. Let's start with DGA. So what exactly is DGA? DGA is an algorithm that, again, we're talking about attackers using AI, right? DGA is an algorithm that malware actually uses to generate random domains that it can then use to circumvent your firewall controls. So when we talk about generating domains, these domains, it may generate, say, 1,000 different URLs. But out of that 1,000 URLs, maybe 10% of that are connected to the actual CNC server. The rest of it does not really resolve to anything. So it is a very common mechanism that you see in a lot of malware that they use to be able to circumvent a lot of our existing security controls. However, as what we've mentioned, there are some specific characteristics to DGA, right? For example, you can generate 1,000 different domains, 1,000 different URLs, but at the end of the day, when they can be resolved, they generally resolve to a small number of IP addresses or possibly even just a single IP address. This is commonly the attacker's IP address or the C2 server's IP address, all right? We also see that most of the time when DGAs are generated, there is a possibility that it is not human, it is not human readable. So it could be, for example, Philippines 123 asterisk alias whatever ABC123 at the backend.com. That's an example of DGA. Why? It's basically used to confuse our existing controls. Then we see that 90% of it cannot be resolved. So that goes to say the same thing as resolving to the same IP. So again, it's just one way that they use to make sure that they can always establish that communication with the C2 server. Then last but not least, it's always single use. You may see this URL in your network today, tomorrow you're not going to see it anymore. Now, the thing is, based on what I've just mentioned, when we do our own, as a human, when we do our own research, we see the URL name, we try to resolve this using whatever DNS servers that we connect to, using NS lookups and things like that. We can decide whether this is a valid URL or not, right? But when we need to do this 1,000 times per day, or 1,000 times every half a day, that becomes a very tedious job. So this is where we actually use our first case for AI. We actually use the AI algorithm to try to recognize the characteristics of DGA within the network. So one of the things that we actually do, So one of the ways we're actually using one of the algorithms that we have actually used in DGA recognition is by using graph analysis. Now, again, this is is again a study of statistics, which again, I'm not a master in. So essentially one of the methods that we're actually using is using graph analysis to be able to recognize the correlation between the first level word used in the URL with the second and the third, to be able to decide whether this is a real domain or whether this is something that was generated by the DGA. Right? The purpose of this is to make sure that we are able to use this to decide whether the traffic is a valid traffic or whether we need to do further investigation for us to actually determine this is a DGA or malware-related DGA algorithm or DGA-generated URL. Right? That's one way of doing it. The other way of doing it is actually using AI, again, to do all this manual work that we talked about. That means be able to resolve investigate all these URLs, the volumes and volumes of URL, and see whether it resolves to what IP, or whether it doesn't resolve to any IP. And once we have seen that, then we have, of course, we look into how we can actually then match back the IP that it resolves to whether it is a known bad IP or whether it is just another IP on the internet, all right? So this is a very simple use case. One of the things that you will notice throughout all the other use cases as well is that many times, once we've understood the behavior of that particular attack, it is something that as a human being, we are able to use our logic to decide whether we can investigate this or not. But many times, when we talk about it, when needing to rely on technology to be able to do this, it becomes a different story. That's why AI starts to play a very important role in terms of cybersecurity, especially in terms of detection, because it allows us to be able to mimic our thought process, our logic thinking into technology to be able to look at all these patterns. Okay? So let's look at another different use case. Now, in this use case, we're talking about trying to decide whether encrypted traffic that we see in the network is good traffic or bad traffic. Right? Now, one of the reasons here is because when attackers attack, they understand, especially if the victim organization that they are attacking, they would know if the victim organization that they are attacking are very cybersecurity savvy, they would know that 90% of the traffic they see internally are all encrypted traffic. So what do? They try to hide their attacks into encrypted traffics as well. So in this particular case, we're talking about a scenario where the attacker compromises one machine internally, using that as a jump host to be able to attack further within the network. So under such circumstances, if they are using encrypted tunnels, things like SSH, things like TLS tunneling and all this, can your existing technologies today pick them up? 90% is no. Why? Because you can see HTTPS traffic coming in. You can see port 22 traffic coming in, but 90% of your organizations has got one very big hole in their firewall, which is port 443 open, right? So we don't know whether it's valid or not without having to look into the contents of it. What we actually do here is that instead of just looking at it by trying to figuring out whether this encrypted traffic is bad or good by trying to decrypt it, which is impossible if you do not have the right keys, we actually look at it from a behavior perspective. Generally, this is what we have observed. Now, again, this is not just something that we develop based on an algorithm because we think we can, but it is also developed based on our experience in terms of looking at all these different attacks, many different versions, many different permutations of these attacks throughout our install base and throughout our own R&D as well. So there are certain characteristics that we have observed when it comes to detecting this type of encrypted communication, especially when it's related to data exfiltration. First of all, there is a symmetry. Once what we do with the algorithm is that we start to study the incoming traffic and the outgoing traffic for that particular compromised machine. So what happens here is that we find there is a symmetry between the traffic pattern coming in to the compromised machine and from the compromised machine coming out, all right? From the other way around as well. So what this basically means, if the attacker is using this compromised machine to steal data, to exfiltrate data, and it's a lot of data, we will see a sudden burst of data traffic go from the victim machine to this compromised machine. Similarly, we will see a burst of traffic almost similar or equivalent in value from this compromised machine going out to whichever destination is supposed to be. So again, this is behavioral based. All right? We're not really looking at it from a perspective of decrypting the data to see whether there's any attack signatures or whether to see they are actually stealing data, but we are looking at it from the behavior of the network. That means we see a burst coming in here, we see similar bursts going out of that machine again, we have to suspect. Now, Whether this is totally accurate or not, I would say 90% yes. There is still the other 10% that sometimes they may not necessarily be accurate. But what it does for you is that it creates an alert for you to pay attention so that you will do the investigation as well. So it's not always about relying on technology to make sure that you get 100% detection. No, it's also about making sure that you are aware that there is such a thing happening. It could be a common behavior in your organization, especially maybe towards the end of the month where you've got high transactions happening just to clear your books for the month, right? But it could also mean something more malicious, right? Again, when we look at it from our logic thinking, we can decipher these type of patterns. But on technology, on machines, we rely on artificial intelligence. All right? So this is another use case that we have used. Brute force attack, again, similar to the previous example, again, but we're just looking at different patterns and different signatures. When we talk about encrypted brute force attacks, now, if you are looking at it from an endpoint perspective, brute force attacks is very easy to see, right? You see in 1 minute, 10 or 15 or 50 different failed login attempts. That's very obviously brute force attacks. But if you look at it from the network perspective, can you see whether it is brute force attack or not? The answer is yes. But if they try to do brute force attack using encrypted channels, can you still see it? With our AI model, with our AI algorithm, we still can. But again, we are not looking at the cause and effect. We are looking at the known signatures or the known behaviors of such activities. All right? So just give you a point to note. A failed attempt, the session for a failed attempt is usually shorter than the session of a successful login attempt. Correct? If you fail the login, that gets terminated. But if you pass the login, you can start doing stuff. So again, we are looking at the patterns. We are trying to understand the behavior of a brute force attack, looking at this perspective. Because it is, again, going through encrypted channels, and trying to decrypt it will be a lot more taxing than actually trying to understand the behavior of it. We rely on this type of information. So for example, the session for a failed attempt, once you failed the login attempt, it gets cut. But if it's a successful login attempt, then you actually start processing. You see the session persists. So again, that's a behavior that we look out for. That's a behavior that we actually configured our algorithm, our AI algorithm, to actually look for. All right? Now, of course, that now does not really become the challenge, because now we are also looking at a situation where we want to be able to detect low and slow brute force attack. Anybody know what that is? So, just in case for those who don't understand, brute force attacks, common brute force attacks, we see a lot of attacks, login attempts hitting the machine, let's say within a short span of time. Low and slow, they actually cut that across longer time periods. Could be hours, could be days, could be weeks. So instead of just relying on that behavior, we have also implemented things like multi-scale time windows serialization, where we actually take a sample of the traffic based on a cut of maybe 5 minutes, then we see 10 minutes, 15 minutes, and so on and so forth, to be able to make sure that we are also able to catch this type of brute force behavior, not just within a short span of time, but also across a longer period, to be able to detect this sort of low and slow brute force attacks. All right? Now, it's not really as boring as it sounds. It's actually quite interesting technology. Time's up, you see? Now they're really fast with that. So let me just go into one last one, which is ransomware and malware, which is actually, I promise this is a lot more interesting. Why? Because first of all, when we talk about being able to use AI, there's two things that we actually do here. Because right now, it's not just about being able to detect current existing malware. That's what signature-based technologies are for. But one of the biggest challenges is zero-day. What exactly is zero-day? 80% of the time, zero-day is just a variant of existing malware, right? Which means you may not have a signature for it, but we already know what these malware behaviors are, right? So what we do in this particular model is that two things. First of all, with our AI, we actually tear the offending file apart to figure out the characteristics and to build a fingerprint of this particular file. Then we actually take these characteristics, we keep a file of it, we keep a note of it, but we also at the same time compare it against well-known malware that we are aware of. so that we can actually, now because it is a variant, there is a chance that there are certain things that they will actually reuse from the previous original malware version, things like propagation method, things like the vulnerabilities that it actually exploits. So when we find a match, we know that this is a variant of that particular malware. So then we are able to detect that malware. But at the same time, we will also update our malware library with this new pattern so that now we have a different baseline, a more updated baseline to work on. All right, so this is a bit more interesting in terms of malware and ransomware. Of course, it sounds easy, right? But if you are studying AI, you know it's not as easy as I make it sound, right? Now, let me just go to, this is UEBA. I'm not going to touch too much about UEBA because it's probably one of the most common use cases you've probably heard of. But it's not that simple. It's not just 5 use cases that we have a lot more than that. All right, so these are just an example of how we use and all the different types of algorithms that we are using. So the key takeaway from here is this. When we talk about wanting to use, when we talk about the dangers of AI, attackers using AI, one of the best methods that we have found to be effective is to actually leverage purpose-built AI to be able to detect some of these use cases, right? And it's even more so, especially when we're looking at it from a network perspective, because there's a lot more information or a lot more IOCs we can pick up from the network. Just to share with you, that's not all we are doing with AI, all right? We are probably only right about here right now, where we are still focusing a lot of our efforts in terms of making sure that our AI engines are becoming more accurate when it comes to detection. But we do have something new that hopefully everybody will agree is quite interesting as well. We are also looking to use AI to start automating security operations as well. That's a very exciting field. Imagine being able to type into your device, your platform and ask a simple question like, how many servers in my network is vulnerable to this particular attack? And imagine having that spit out the response spat out to you in the same way as you would using ChatGPT. That makes it a lot easier for you to be able to find out more information about your security landscape. And also, we are looking at using AI to actually automate security operations processes from investigation right down to coming out to conclusions and down to remediation as well, and then establishing what that thought process is. So these are all still something that we are working on and should be out soon, but it is a very exciting time to be actually using AI in cybersecurity. All right, so before they physically come and chase me out, I probably need to say thank you. And it was nice to have your attention for such a short period. So if there's anything else you would like to know, I'll be around to be able to have this chat, to carry this chat further. Thank you very much.